introduce you about our design and analysis of the common source amplifier circuit. This is our circuit design diagram considering about the advantages of each. We used normals with width equal 10 mm and length equal 0.18 mm to maintain a good balance between linearity and gain, and the input impedance exceeded is 500 kiloohms. The frequency response remained flat below 1 MHz. All these targets were successfully achieved, however, the measured voltage gain was about 15.2 dB, which was lower than the expected 20 dB. This shortback might be caused by several factors. First, due to the power supply limitation, the RD cannot be further increased. Second, the GM might still be too low for the desired gain. This could be due to an insufficient WAR ratio or an unsuitable operating point. We have not conducted detailed simulation on these factors. Despite these limitations, this is our best solution before the report's deadline, and we will continue to optimize the design based on feedback from our teachers and classmates. Thank you.
The common gate amplifier is often used in some applications where lower input impedance is required, like RF systems. This is my circuit design. I add a resistor in parallel with the source to reduce the input impedance, and a capacitor in parallel with the drain to meet the bandwidth requirements. The figure is the small signal equivalent circuit. Here, I assume that RDS is very large. Based on this, the calculation results are shown. Then I test the input resistance. The results are equal to the previous calculations. The next circuit is used to test the output resistance. The result is 450 ohms, which matches the calculation, indicating that RDS has a minimal impact on the output resistance. 3 dB bandwidth was verified. According to the previous calculations, a 0.07 nanofarad capacitor was added, and the measured 3 dB bandwidth turned out to be 5 MHz, which matches the expectations.
Now, I will briefly present our project on the common drain amplifier design for this course. The common drain amplifier offers two main advantages. First is high input impedance, which is ideal for interfacing with high impedance sources. Next is low output impedance, making it suitable for driving low impedance loads. We first designed the classical common drain amplifier circuit and then use LTSpice to simulate the circuit, just like the circuit design diagram. Then analyze its small single equivalent model. To validate this design, we conducted both input and output resistance tests. The results confirm that the amplifier maintains a high input resistance and a low output resistance, consistent with theoretical expectations. Next, we'll see input resistance, then its output resistance result, which is 99 ohm. Regarding the frequency response, our simulation shows that the amplifier maintains a flat gain up to 55 MHz. This bandwidth is quite impressive. However, to improve the gain, we had to increase the NMOS width, which introduced more parasitic capacitance. This caused some discrepancies between theoretical calculations and simulation results. In conclusion, the common drain amplifier performs well within its intended frequency range and meets the design goals of impedance and gain. That's all. Thank you.
The advantages and limitations of common source CMOS amplifiers are shown on the slide. The noise ladder in limitations means that CMOS amplifiers are noisier at low frequencies, which may affect signal fidelity. This slide is about common gate CMOS amplifier. This slide is about common drain CMOS amplifiers. One of the limitation, voltage gain close to 1, means that the voltage gain of a common drain amplifier is usually close to 1, which means it does not provide significant voltage amplification, only current amplification. This slide shows the difference between these three amplifiers, and it also shows that which field does each amplifier suitable for. Thank you for listening.